Thank you very much. So, okay, first of all, thanks a lot for the invitation, for letting me speak. So today I will talk about regularization by noise for reaction-diffusion equation. So just before starting, I want just to tell you, I mean, like some of the techniques I'm using actually has been studied by Flandolier's collaborators in the study of regularization by noise for other equation. But what was the point somehow of my research was really to just show that also in this context you can benefit from using LP theory and of course with P larger than 2, because most of these techniques are just be built for the Hilbert space theory, and I want just to show that LP actually is quite useful and you can really benefit from it. Okay, this is just the start. So this is like the outline of my talk. So I will first try to give a brief introduction of reaction-diffusion equation, and to start to just to give an idea of what they are, and then I will just introduce the noise, and then I will just taste the result and giving a brief sketch of the proof. I mean, let's see how far I go, and then at the very last I would like to talk about some open problems, because I mean this is my starting point was not really reaction-diffusion but Navier-Stokes, but there are like some problems in doing it, so I would like to discuss, I mean, to see what actually LP can also be helpful for Navier-Stokes, but there are still some limitations because of some regularity issues. Okay, so but let me first start with the reaction-diffusion equation. So they are quite really innocent equations. So there are a system of parabolic PDEs. So when we have this index I, which basically can go from 1 to a big an integer number L, and you have these nu, which are like the diffusivity of each component, which and you have some nonlinearity. So it's important here that the coupling only goes through the nonlinearity. So V1 and V2 are just linked from the nonlinearities. And okay, when I don't put subscript, it means that I take the full vector. Okay, so as you might know, they appear a lot in biology, ecology, chemistry, and population dynamics. But I just want to give one example, just to give an idea of what kind of nonlinearity you can face while studying this equation. And these are coming from chemistry. So if you have some reaction, there is like this, there is like a principle which is called law of mass action, which gives you the specific form of the nonlinearity you have to put in the equation such that the concentration of your reactants action obeys to these PDEs. So as you can see, this looks, I mean, if the coefficients are big, these are a polynomial which are really, I mean, locally are really smooth, but they grow really fast. So the problem is actually the growth of this coefficient, and as we will see, this will give some, the high growth at infinity of this V will give a lot of trouble. Okay, so but just for this talk, I will just use all over again one parameter, which is this age, which is basically the growth of this nonlinearity. So there is the only parameter you can you might want to keep in mind. And in the talk, I will just use 3 assumptions, so I don't really need the specific structure of the nonlinearity. We need just a polynomial growth, a mass conservation, because we at least expect that the mass of the reaction will not blow up in finite time, and the positivity. So for instance, this basically is telling you is that if the height reactant is not there, it cannot go below 0. So this is just the mathematical way to say each component doesn't go below 0. Of course, in some sense, if there is no that reactant, it cannot be consumed by the reaction. Okay, so as you may expect, immediately the picture on local and global well-posedness of reaction-diffusion equation is quite similar to the one on Navier-Stokes, with some kind of perturbation. But somehow the idea is always that you have a local strong solution which you can construct by using a fixed point argument. And the life of your solution is positive, but it's small, and you don't know really how big it is. So this basically, you just have to choose a function space, you do a contraction argument, and that's it. Now the question, as for Navier-Stokes, is that is this time infinity or not? Here the situation in reaction-diffusion is quite more explicit. So there are some counterexamples to the global existence of this system. here in this paper is not really the torus, so there might be a chance that, I don't know, like on the torus there are some more cancellation that nobody have seen so far, but as far as I know, there is the geometry really, it's not clear, but here they use some kind of transformation on bolts, so they need some radial coordinates to make the blow up happen, but yeah. I mean, in principle, there is no easy a priori estimate or cancellation that you can see that will help you. And the reason why is that the only control that you have along the evolution is the mass. And the mass is really like just an L1 norm, which is really like a poor estimate if you want to control like this f of v, because the f grows really a lot, and this is basically doesn't say that anything about the nonlinearities. Okay, so if you have like some entropy dissipation condition on your reaction, you might have some kind of renormalized solution in the sense of the parallel ion, and this was this work by Julian Fischer in 2015. So this was somehow you can think it as like the counterpart of the Ray solution for Navier-Stokes, although I mean like actually the normalized solution are much more weaker than but this is kind of to make a parallel with the picture of Navier-Stokes. And yeah, so somehow the overall problem is that you have like, as Navier-Stokes, you have some global solution which are not really regular, and you can have you have no uniqueness in this class, and then you have some local solution which are smooth, but they just have some finite time. I mean, they exist in principle only up to finite time. So now, as you can, as the title suggests, we would like to put some noise to improve the situation in some way. So it's not clear what we want, but before going to that point, we should actually ask what kind of noise we have to put in the equation. I mean, it's not clear, and for instance, additive noise is not really a good idea, because if you put additive noise, then the additive noise already in the stochastic heat equation, you can get a negative solution, which in case of chemical reaction wouldn't make really much sense to talk about negative solution. So you have to be a bit careful. So what is, I mean, like, I like it a lot, but I hope that this is also convincing you that transport noise might be quite helpful in this context. But what typically reaction diffusion are happening in a fluid, and therefore somehow the fluid is doing something about the dynamics of the flow, and especially in the engine of plane, they have seen with experiments that if the flow is quite turbulent, then there is the effect of the turbulence is that the reaction actually happens in a better way. So somehow there is some enhancement of the reaction, just because all the reaction can see each other a bit more. This is kind of the idea, because if the fluid is turbulent, there is no structure of the fluid, so all the reaction, whenever they will meet with more probability in some sense. Okay, so somehow we want to put in our model also the action of a fluid, and therefore you have to add a transport term. Okay, I'm talking about incompressible fluid. So this is, you just put a transport term, and now the problem is that, okay, now this U should be a solution of a Navier-Stokes equation, or I don't know, like some other simplification of model, but these are of fluid dynamics equation, but these are usually quite expensive to simulate. So somehow you want to just put something which is somehow resemble a turbulent flow, but it's not really the solution of Navier-Stokes equation. And then what you can do, you can just put something which in some sense is actually close to a turbulent flow, or what you expect to be a turbulent flow. And yeah, somehow you put, which sometimes is kind of standard in stochastic modeling, you assume that your U is actually somehow white noise in time, and there is some coloring in space. So the sigma are actually, they have some decay at infinity as kappa goes to infinity, and this decay is actually can be related to the correlation function of your fluid. So you can actually design the sigma so that you kind of get some statistics of a turbulent fluid. But this we will not put I will not put any attention on it. But usually you can check that at least on the torus there are quite explicit construction on the Krejcik noise. Okay, so for me, I will assume that this is actually a good way to model the turbulence, and then I will insert in the equation, and then I get what you can expect. So I have the same equation as before, plus a stochastic perturbation, which is of transport type. transport just because this we have a sigma which is transporting like our v. Okay, actually these things can be made rigorous, like that transport noise actually appears as a in some way, and then there is like a nice paper by De Bush and Papaletra. Sorry, I don't know. I tried yesterday, but and yeah, somehow where they derive like fluid dynamics equation, not exactly the reaction diffusion with transport noise, by assuming that somehow you have two scales, and on the small scale you have some kind of additive noise. You have to do some rescaling, and then effectively you have like an SPDs, with transport noise. Okay, so there is like I mean, there is a way to make this a picture a bit more rigorous. Okay, so and this is kind of the motivation. So I will look at I would like to see now that actually how it is that there is at least a choice of my turbulent of the sigma, for which I see something which is kind of close to an enhancement of the reaction, or that it actually improves the reaction. Actually, you can. So but I need to introduce a bit, not two new parameters. One is nu and one is theta. We will see later what kind of role they have in the proof. But for the moment, let me state the theorem. So the theorem is a bit, the statement is a bit, it's not completely straightforward, but somehow you have to fix up an epsilon and a time, an horizon time t, and then you can choose theta and nu such that the probability that my solution lives up to this time capital T is larger than 1 minus epsilon. So I cannot really reach 1, but you can ensure that the solution to the SPDs live for a long time up to an epsilon. Okay, and what is somehow nice of the argument behind this, at least for me, what is nice behind this argument is that actually when you prove this, actually you prove something slightly stronger, is that your equation is, I mean, the solution to the SPDs, which is actually close to a deterministic PDE with more viscosity. And this new viscosity actually is this one that we put here, okay? So somehow there is a relationship between this nu that you see here and this nu that you see here, somehow, and this close is a bit, you have to choose what kind of, in which sense with these two, the solution to these two PDEs are close, and what is somehow kind of related to the physical picture is that they know that there is some enhancement of your reaction diffusion, and this is actually what happens, at least in this norm, okay? So we will come later how this new Laplacian appears in the equation. So what is kind of, the 2 points is that actually this time can be really, really large, and it works for the example that Pierre and Schmitz they have in this paper, although the geometry is not the same. So that's kind of the disclaimer. Okay, so of course behind this result there is like an improvement of the bounds for the solution to this reaction diffusion equation, and so now the question is in which norm you get like this improvement of the bounds, and more importantly how you can really improve these bounds. Okay, so there are these two questions, and for the first part, for now I want first talk about what kind of norms. Okay, no. Okay, before going there, I would like just to make a remark that actually the usual energy estimate are not a good idea here. So somehow if you start trying to see the action of the noise at the level of energy estimate, you don't see anything. For instance, what I mean is that if you try to compute any LP norms, you will see immediately that the noise doesn't give any contribution. So in the end, because it's a transport, so any kind of object like this are basically zero. So in the end, you will, when you write the Ito differential of this process, you see basically the same identity you see without the noise. So in principle, you don't see any really contribution appears from the LP balance, and therefore there is no really easy help from the noise. This is because actually the statement is not that for all transport noise we can improve the situation. There is just a specific noise that will help us, and this is because energy estimates are not really fine enough to see the creation of small scales of the fluid. Usually, from people that study mixing, the good norm is H-1. So, and this is kind of related. So somehow, what the things that happens here is somehow happens below the energy level. So when you are a bit below the energy level, you see something that somehow the turbulence is actually helping you. But if you really look just energy estimate, there's no way to get it. But before going really to see the help of the transport noise, now we have to go to see what kind of norms we have to put in which kind of norms we have to put. So, and usually when you have to, when you have to study a nonlinear heat equation, it's a good idea to start looking what are the critical space behind them, because usually criticality is really like a line in some sense in the class of function spaces. Above the one, you are subcritical, so your life is somehow easy. You can do like a fixed port argument, at least in this simple case. On the critical line, you have some hope to get a local solution, and when you are supercritical, there is no hope for a local well-posedness of your equation. So, as I told you at the beginning, I have like some parabolic equation which has some linearity that grows like age. So I want, and then locally somehow our PDEs behaves like this. Like this nonlinearity equation on the whole space. So it's just if you scale our problem, you should really look. The dominant terms are this one, and for usually in parabolic PDEs, you try to see when you want to compute the critical space, you start wondering what kind of rescaling leaves invariant the global solution to your equation. So in space and time, you just use the usual parabolic scaling. And if you match the power on this lambda, you get some number, in which case is 1 over h-1, for which the set of global solutions are invariant. And now the space of the critical space, and indeed the space which are are the space of initial data, which are invariant under this scaling. So if you just compute the time is equal to 0, you get this map. And basically now the question is that what kind of spaces are actually invariant under this map. One class which you might want to study are LP spaces, and usually one good in the scale of LP or LQ, there is only one Q which is good enough for making this work, and you compute it just by easy change of variable, and this number comes out. So this number depends only on the growth of your nonlinearity. And what is nice about this number is that there are actually also connection with the Fujita exponent that was mentioned I think at the beginning of one of the first day. So somehow there is in the case of heat equation on the whole space, there is a number which is called Fujita exponent, which is from which below this alpha, there is no hope to okay, this one is on. Below this number, you cannot prove even for small data global solution for this equation because of certain reason, but at least for small data, you can prove global well-posedness, and if you check, this number is only when this power is less or equal than 1. So basically means that when you have a failure of the usual harmonic analysis techniques, you basically might end up in a blow-up problem somehow. That's kind of my intuition behind the Fujita exponent. So indeed, when you have like the Q larger than 1, you can easily prove that the small implies global, as in Navier-Stokes. Okay, so but this is now we have understood the scaling. So the scaling is the space is this one, so you have L infinity in time and this exponent in the space, and this is good. It's critical for having, it's rich enough to have local well-posedness. Okay, so if we have so somehow coming back to the reaction-diffusion equation, if you have an estimate in a space which is richer than this, we get immediately global well-posedness. And now what this means, rich, from what is my understanding, rich means that you can your Sobolev index, which I will introduce in a moment, is better than this one. So the Sobolev index, you have seen sometimes, like by using this Regularization serine probability condition, is this kind of number. So you have like these two. If you have a space like LR, LQ, the number associated, which is called a Sobolev index, is this 2R minus 2R minus the D over Q. This is still linked to the scaling of your function spaces. And in Navier-Stokes, for instance, the Regularization probability serine means that the number for the scaling in Navier-Stokes is -1, and this should be -1. And this, you get that kind of condition. In our case, it's not really -1, our scaling, but our number that scales is really this -2 over h minus 1. So we have to find a space, I mean, to be able to get some global responsiveness to show our delay blow up. The space should be at least richer than this space. Otherwise, we are too low. So somehow that's why we cannot use L infinity in time L1 in space, because it's already there by the mass balance. We have to use some Q which is larger than that one. Okay, here I didn't put the equality. In principle, this is the critical condition, but because at some point I have to use compactness, so I have to lose a bit of smoothness, and then I will go, if I am equal, I will lose this epsilon, I will be supercritical. So that's not a good idea, but this is not clear from now. So now I have understood what kind of space I have to use to at least be able to get the result. Now we have to show how I get the result. Okay, so the idea now is to take our equation, take R, which is really, really large, and Q, which is larger than this threshold number, such that you have a Sobolev index which is better than the one that we want, this -2 over h minus 1, and then we use a cutoff function phi. So somehow we are just multiplying our nonlinearity in a way that when this norm really gets really, really, really large, we cut the nonlinearity. So in principle, this means that when this term, somehow, if you really look at the scaling now, this term is kind of sublinear because we have cut it in a space which is rich enough, okay? So, and then now, when you put this cutoff, there is no problem for this equation, but of course, it's not the equation we want to study, so we have to remove this cutoff in some way. And this is kind of where the main step of the proof comes, which is called usually scaling limit. So the idea is that, of course, this trick is quite known, so you have to rewrite this transport noise in Stochanovich form as in two pieces, like a deterministic part and an autocorrection. And as you see here, this appears this new Laplacian, but it's actually just a fake Laplacian, because if you try to do any kind of estimate with Ito, this Laplacian will be just cancelled by this martingale. So somehow, there is, at this level, there is no additional dissipation. So we have to somehow get rid of this M, and you can do in a certain way. So, and this is actually the key point. So the martingale part of this identity goes to 0 in a very, very weak norm if you keep constant this theta in a little L2 and you go in little L infinity, you go to 0. Okay, this might be a bit technical, but actually I want to make a point afterwards about it. So we will really keep like this little L2 is equal to 1, but we send this to 0. We can do it because, of course, the embedding of little L infinity in little L2 is false. So you can build such a sequence such that, and actually we want really to do that. So we want to pick a sequence which has this little L2 is equal to 1 and the little L infinity going to 0, such that we hope to that in this way, if we can really do like this limit, we will end up without this martingale part, so eventually to this equation. So if we can really do that, I mean, if we can really find I don't know, in some way we can really show that this Vn, which are the solution to these SPDs with this theta n, are actually converging in some space that we want, this LR, LQ. Then actually we have to converge to this because the martingale part is actually going to 0. Okay. So now at the very end, if you believe that this limit is okay, then you can remove the cutoff. So the remove the cutoff because you can now tune this new viscosity such that the limit equation is good, and you know that actually in this norm you are close to this value, and then you can remove it. Okay, so this is just actually really the sketch of the main result, but the main point somehow in all the business is really now we have understood what kind of space we have to use. So this is LR with values in LQ with a good Sobolev index, but now we have to ensure that you actually get a limit, and this limit you can do it, for instance, by compactness. So if you want to use compactness, so you need at least to be able to do an a priori estimate in a space which is better than your LR LQ. Okay. So what is really the point is that now the nonlinearity, since we are doing this limit, when we put the cutoff on the equation, there is no problem anymore at the level of the nonlinearity because it's already cut in a good space. So you see now what is the problem here, and the problem comes actually from the sequence. So the sequence actually makes our noise really, really bad, in the sense that the only control you have about this sequence is only in L infinity with values in little L2. So basically, you're basically converting your problem from some problem which has like a bad nonlinearity with a problem who has like no more nonlinearity but has bad coefficients. So somehow this is kind of similar to PDEs with L infinity coefficients that you just basically have like you have to show estimates when you have a PDE with measurable bounded elliptic coefficient, with of course in the deterministic case, and this is studied a lot in the by Moser, Nash, and De Giorgi. But in the PDE, in the SPDEs are a bit not known. I mean, there are many results which we don't know. In our case, indeed, we use kind of a Moser iteration. Konstantinos and Mate, I think you had some papers about De Giorgi. I mean, yeah, at least in the case of, you have the Moser iteration for linear SPDs, but this is kind of the same idea. Indeed, for this kind of equation, you can use some kind of Moser iteration to get enough bounds for Q really, really large. And this is actually explain why this argument only work if you, I mean, the overall argument only work if you stick within the LP setting, because if you try to do this with L2 base space, you have to put a lot of smoothness in your space, and you have no chance to prove any estimate if you just assume no smoothness from your coefficient. So you have really to stay in LP, and of course LP estimates for an infinity coefficient are not super easy to find, but there are still some. Like for instance, in the case of a scalar equation, because here we can basically work component-wise, because our operator is actually there is no cross diffusion in it. But yeah, okay. So this is kind of the picture, and what is like as I mentioned at the beginning, this, I mean, the scaling limit itself is of course not my idea, and I think the first time it has been used in nonlinear SPDs is by Flandre and Luo, and then they have like, that was originated in a paper by Lucio Galeati, and they have also this joint paper about the A-blob. So somehow, and what now that if you look at what you have seen in the talk, basically the last paper, which has like a more general framework, is basically telling you if you have a PDE which is badly behaved, that is such that the L2 space is not critical, I mean, is subcritical, then you can prove the label up. So this is kind of the I don't know, functionality way to see this paper. In our case, we have to use some more elaborated argument. The energy estimate that to prove compactness is not enough. You have to use more the LP structure, like and also like it took me a lot of time to just realize that actually this LR LQ space was the good one, at least that it works, because this was not really the first example you can have in mind. And yeah, so somehow, as I repeated before, as I said before, the central thing is to really use some kind of Moser iteration to get the estimate. So what is like, again, like to just close with a more philosophical kind of consideration, is that I was just always wondering why, what is kind of, is there any kind of physical intuition behind this scaling limit? And actually, I mean, in some sense, if you really look close to the equation, to this scaling procedure, you kind of get that this, and also is kind of a similar to homogenization result, because if you remember, the transport noise is actually a model for small scale, and what you do usually in homogenization, you have this small scale that you want to kill by letting this parameter of the inhomogeneity to 0. In our case, this parameter was this theta. So we want to kill the, and then effectively what happens in homogenization, you get something which is, in the end, you use some ergodicity, but in this case, you get something at the limit that is deterministic. Okay, so here I anticipate myself, but since it's a model for small scales, you get that somehow this scaling argument is really like zooming out from small scale. Okay, so and if you really are familiar with the homogenization language, I think that you can think as the deterministic, the limiting equation as somehow an effective equation. So it's, if you want to simulate your SPDs with and you are happy with these norms, then you can just simulate this because they are close. But what is this enhanced diffusion is actually what they call large-scale regularity. Okay, so in the large, you see something which is much better than what you expect. Okay, so as I mentioned at the beginning, what was somehow the main idea was to start doing it for 3D Navier-Stokes equation. But of course, what is the major problem is that if you look at the scaling, the estimate you should need is something like LR L3 plus, because I'm just using 3D, so I don't care about more higher dimension, which is much smaller than what we have seen, because in our situation, Q can be really large depending on this age, and yeah. Of course, the problem with Navier-Stokes is that you have the pressure that you have to handle, and the pressure, of course, is a non-local operator. So many, like for instance, there is no chance you can have something like Moser iteration in that scenario. But of course, we need a Q which is way less than infinity. There is some hope. I mean, if you really think that the homogenization parallel is a good idea, then actually you should compare your the regularity theory for SPDs to the regularity theory for PDEs with bounded measure coefficient. Actually, there's been like some progress in the case of the generalized Stokes operator in the deterministic case, so you cannot really use it. But I mean, half of me thinks that it's a good idea to keep on going. But yeah, so this is kind of a good news, but it's at the moment I have no clue how to get something close to 3 in that case. And yeah, well, what is, of course, we would like to do now is to just get something which is somehow, now the point is that somehow LP theory for SPDs are quite helpful and with L infinity coefficient, but it's completely, I mean, there is not much going on there. I mean, like, for what I know. Okay, but what I'm doing now is actually to try to at least get like this capital T that you have seen in the main statement to be plus infinity. You can do, but you need some more structure because you want to use some compactness argument. So you have to understand better what is the long time behavior of your chemical reaction. So for instance, you can, in the case the chemical reaction is balanced in some sense, you get some L1 decay at infinity with entropy dissipation inequality. But yeah, so this is the only thing that I feel it's now feasible in this scenario. Okay. With these are just a few references, and with this, I would like to thank you for the attention.